day, and I'm going to cover a few topics. The first topic is GAN. We need to, well, I will talk about the SAGAN, BigGAN, BERT. So that I want to show you a paper, network to network. Let me show you, okay. This is network to network. You see, the paper was published by Professor Omar's lab, and the 1, 2, 3 works, you can see they are continuous. And if I want to clearly explain latent diffusion, then I think the best way is to talk about their first paper, network to network. Then we can see the relationship between the two papers. Okay, and in our previous week, we talked about the VQGAN, and the VQGAN is an extension of VQGAN. And what is VQGAN? VQGAN is the second paper of Professor Omar's lab. So I talk about so many related papers because I want then converge to the latent diffusion so that you can understand, what latent diffusion does and what you have experienced using the stable diffusion. It is based on the latent diffusion. Okay. So, and I will also talk about the PyramidCLIP and the OpenCLIP because CLIP is used in stable diffusion. And after CLIP was published, some researchers, they want to improve CLIP or modify CLIP to generate a better result. And PyramidCLIP and OpenCLIP are two of them. Now, this is a very complicated chart. Okay, so let's start the trace. SAGAN, and later become SAGAN, and SAGAN will become BigGAN. And almost at the same time, Google released the BERT. BERT is a language model. And BigGAN and BERT combine them together, and it becomes network to network. It is a text to image generation model. Okay, this is our first trace. Okay, so let's talk about what is SAGAN. Let's go back to 5 years ago. And there are some state-of-the-art methods they call SNGAN. SNGAN means spectrum normalization GAN. Okay, and there is also another method called projection discriminator. So one is, so you see GAN, there is a generator and a discriminator, right? And SNGAN means they apply spectrum normalization on the generator, okay? And projection discriminator, they improve the discriminator using some technique. So, and both papers were published almost at the same time, and from the same group. So it's a very interesting. They found a very useful way to improve the two parts of GAN. All right. Suppose, okay, there were the state-of-the-art method in 2018 early, and then okay, the SNGAN means based on the two state-of-the-art methods, they want to introduce or add self-attention to the CNN-based GAN, just this, okay? And they also introduced the imbalanced learning rate for the generator and the discriminator. The imbalanced learning rate was not their invention. They just used somebody else's findings in their SAGAN. So the SAGAN means S means self, and A means attention. So idea is straightforward. There are some existing methods, and they are self-R. So, and self-attention in 2018 is a relatively new idea, and they are just wonder if they apply self-attention to an existing state-of-the-art method, what will happen? Okay. So this is their approach. So you please see this figure. If you remove the non-local layer, then it is the state-of-the-art. So what they did was they add a non-local layer implemented by self-attention to a certain feature map. So because this is GAN and this is output image, so in the beginning this is a latent variable, it's a noise. And they are upsampling. So they just insert a self-attention layer at a certain feature maps. Okay, and it adds the feature maps back. So this is the definition of the self-attention. And if you okay, do you still remember self-attention? We saw the definition in our previous lecture. So that is, if there is a query vector and there is a key vector, then the query vector or key vector or matrix in their time, they will generate the self-attention value. And the self-attention value is the softmax of those inner products. Okay. Then it can be viewed as weight. The weight will be applied to the value. So V is the value here. Then this is to adjust the vectors or matrix. Okay, so the self-attention, because this is a generator, there are low resolution layer, middle resolution layer to high resolution layer. They just pick one of them so that we have the feature maps already. Okay. From the feature maps, they create the query matrix, key matrix, and attention matrix, and then do self-attention, and then create the self-attention feature maps. And then they add the self-attention feature maps back to the existing convolutional neural networks map. Okay, so they use ImageNet to do the experiment. So in the ImageNet dataset, there are 1,000 classes and 1.28 million training images. And okay, so they use 4 GPUs and run 2 weeks to generate an image size of 128 square. So why it takes so much time to train the model? Because self-attention is a very computationally expensive step. And let's see their experimental results. Okay, so this is the SAGAN, their proposed method. And you can see this is a feature map of 8 by 8 pixel. Feature map 6 by 16, 32 by 62 by 2, because they want to generate an image of the resolution 128 square. So this is different upsampling steps. Okay. So, and because self-attention is very expensive, so they in 2018 they only can apply self-attention to a single feature maps. Okay. So they try different feature maps and get the result. They found if they apply the self-attention to the feature maps of 32 by 32 pixels, they get the best FID score. But the best inception score was generated for the 4 by 62 feature maps. The residue means if they replace, okay, let's take it back to here. Here is the self-attention layer. If they replace the self-attention layer with a convolutional neural network, then and because the value will add back to its feature map, so it equivalent to a residue block. Okay? So here they show if they use self-attention, the results are much better than the residue block. It means self-attention layers really can improve the model. Okay, so the spectrum normalization GAN plus the projection on the discriminant data was the state of the art in 2008. And this is their inception score and FID, so that SAGAN shows use self-attention layers. Then the inception score was improved, and the FID is also improved, the lower the better. So, okay, these are the images generated by the SAGAN. Okay. From our perspective today, the results are not very good. You can see that some of the goldfish looks very weird. Okay, and but however, they were the state-of-the-art result in 2008. And yeah. So the two number here, this 44.4 is the inception scores for SAGAN, and the FID value for inception SAGAN, and the 55.1 is the inception FID value for the SNGAN. Okay. Because ImageNet have many classes, so for those 5 classes, in SAGAN performs better, but there are some other classes SNGAN performs better. And the table here we see is the average result for the 1,000 classes. Okay, so they provide the image to illustrate why SAGAN works. Okay, so how to read the paper? Okay, see there are 3 points, a red, a green, and a blue one. It means if this is the generated image, and if they pick up 3 points on the generated, and then they see their previous layer, okay, and because this is a self-attention, method, so they can highlight which region in the previous layer contribute to the final layer. So you can see from this region we can see some nearby regions contribute to the red dot. But for this, you see the green dot is here, but this is somewhere far away, non-local region. It will contribute its value to the red dot. It is impossible, I should say, if we use the convolutional neural network-based method, it cannot generate the result, because CNN only can get information from nearby region. But for attention, because attention see everywhere of the image, so it can contribute its value to somewhere far away. So this is the improvement generated by self-attention. It means the non-local model. Okay. So this is the reason in this paper they call the block non-local, okay, rather than self-attention, because from their perspective, self-attention, the meaning of self-attention is just non-local, I should say non-local model. Okay, so after SAGAN was published, it became the state of the art. And the BigGAN, their idea is, okay, so let's go back to the slide. Okay. SAGAN was published by Google. And there are some researchers in Google. They wonder, can we improve SAGAN? So that is the motivation. And okay, how to do it? They want to modify the SAGAN so that it can generate higher, larger images. So, okay. And let's pay attention here. To do it, they need the TPU. Google TPU V3 part. This is a very, very powerful machine. Okay, and we don't have so much computational, computational power to do it. So we can only read their results, but it's very difficult for us to reproduce their results. Okay, so they tune some parameter. So this is the setting for SAGAN, the batch size, the number of channels, and okay. So they tune the batch size. If they increase the batch size, then FID just slightly increase, it decrease. So it means the number of batch size matters, and usually the larger the better. Okay. And if they double the batch size again, they found the FID still decreased. It's good. And if they okay, so to the batch size of 2048, it is achieved the best result. And then they tune the number of channels. Because you see, SAGAN is a convolutional based GAN plus attentional layer. So the number of channels, it is a hyperparameter for the convolutional network. So it also can be tuned. If they increase the number of channels, they see the number of parameters increased significantly from 81 million to 173 million. However, the FID also improved. So it is good for them. If you have sufficient computational resources, you can tune your model to generate very, very good result. And then now they introduced, now they modify the architecture. Here, the shared embedded means, let's go back to the slides. In SAGAN, the latent variable Z only applies to the first layer. So they modify, they insert the latent variable to every layer, not only the first layer. it means the shared embedding. Okay. And if they apply the shared embedding, they slightly reduce the number of parameters and improve the FID value. The skip Z means, okay, here. Oh, sorry. What I talked about there was skip Z. It means connect the noise vector to every layer. That is skip Z. And shared embedding means connect the collect conditional vector to every layer. So the concepts are similar, but they are used for different input vectors. So apply the shared embedding and skip Z. They also improve the FID. And finally, they found that if they apply the orthogonal regularization, the FID also improved. So what does orthogonal regularization means? Because there are a lot of parameters, right? And do you still remember the meaning of regularization? I remember, okay, we talked about in the middle of the semester. It means we sometimes want our parameters have certain properties. For example, if I don't want them too large, then I may apply a one norm or two norm regularization term, so that my model, part of the loss is the reconstruction error, and part of the loss is the regularization term. So that it is a balance between the reconstruction error and the normalization term. So here they apply an orthogonal regularization. It means if you the W is the parameters, and they use this form, it means they want those parameters will orthogonal to each other, but they don't restrict the length of the orthogonal to 1. Okay, so the original orthogonal regularization means all of those vectors should orthogonal to each other, and all of those vectors should have a unit length. Okay. But they found the performance is not very good, so they slightly changed the definition here. They only want those vectors to orthogonal to each other, but they can be any length. So if you use this term, the 1 means is a square vector full of 1. So you can see this, okay. And the minus the unit matrix. So it means a matrix on the diagonal, every value is 0. And for other elements, the value is 1. And if we have the regularization term, it means the operator here means element to element multiplication. So it means what? It means it expects the W, they will be orthogonal, so that their diagonal will be 0. Okay, for other elements, they don't care about so much. Okay. And this is the BigGAN architecture. So from there are several architectures, and this is for the 255 square output image. Okay. So given a random noise input and an embedding vector, okay, the embedding vector, they do the experiment for the image net. So there are 1,000 classes in image net. So given a class label, it will convert the class label into a vector of 128 dimensions. Okay, then first they will combine the 128 dimension plus 20. 20 means the only use 20 dimensions from the latent variable. And other sections will insert into those rest block. Okay, so that is the meaning of the this skip Z. So section by section insert into the dimension. Okay, then there is upsampling from 4 by 4 to 16 by 16. 8 by 8, 16 by 16, and 32 by 32, 60 by 64, 128 by 28. Therefore, this is the non-local block for 128 square. So it's almost the same as SAGAN, but it becomes larger. Okay. Then finally, they will generate an output image. And this is the discriminator part. Okay. So let's take a look of the generated image. So they found running through the 1,000 classes, some classes are easy to generate. They show, for example, dog, library, what is it? Lemon, and clip. So they found for easy class, they share some common properties. If they are mostly pictures and there are a lot of training examples, then the generated images usually have good quality. But they also found some difficult classes. So I think this is the most interesting part. If there are unlike the human faces or crowds, or if the image contains many dynamic and structured objects, okay, and have many details meaningful for humans, then they generate poor results. So you can see, because of our vision, our eyes are very sensitive to human faces. So if there is something wrong, we easily spot them. Okay? And we also know, for example, this French home, their lines, those tones should be well aligned, vertical and horizontal. But once it generates the tiered tones, then we can easily spot them. So let's see this. Okay. Oh, and also here, our eyes are very sensitive to human skeleton structure. So if there is something wrong, we easily found, oh no, this is not the human body we are familiar with. Okay, so in your homework 4, Dr. Chen Bo-Rui, he shows this is the correct image. And this is the image generated by ChatGPT. Okay, so for us, we easily see something wrong. Why? Let's see this. Is there some meaningful detail for humans? Yes. Those English words are very has special meaning for doctors. So they easily spot something wrong. That's not correct. Is there any structured objects in the image? Yes. All those organs should be structured. The location, the size, and the orientation should not be altered. They should follow some patterns. But the generated image doesn't follow those patterns. Okay, so that's the problem. And another image, same. This is, excuse me, both of them generated by ChatGPT. Okay. So thank you. So what I want to show you here is the problem not only exists in ChatGPT or DALL-E E3, it also happens in GAN system. Okay, so How to solve the problem? I don't know. Okay, so this is a research topic. And I hope someday I can read some papers. They propose some useful method to solve the problem or reduce the problem. Okay, and in BigGAN, they also found an interesting technique. They call it truncated normal. It means the GAN ideally should render images from a random noise in the normal distribution, ideally, okay? But if they set a truncation value t, it means if I sample a noise signal z, and the magnitude of z is greater than t, then they just shrink it to a small value. Okay? Use the truncated noise to generate the image. So this is the result. If they set t as 2, then you can see there are 4 dogs, and they look very different. If they set t as 0, the 4 dogs look slightly similar to each other. And if they set t equals to 0.5, they look more similar. And if they set t is a very, very small, it means because the t is small, the noise value cannot be, will be very close to each other. Therefore, their generated result will be similar to each other. So it can make sense. So what's the meaning of the truncated value? It means if they want to increase fidelity, it means the generated image just look like the class. Okay, then they can apply the technique. But however, if they reduce the range or the area of the random voice, then they will lose the variety. The generated images won't be highly various. Right, so here is the BigGAN, and the BigGAN was very, I should say, influential for the GAN community for many years, because it is very big. It can generate 1,000 class images in 1,000 classes, and it is very expensive because they are researchers at Google, so they have the computational resources to do it, but for others, it is very difficult. All right, so now I mentioned in 2008, Google published BigGAN, and they also published BERT. And what is BERT? So let's go back. This is transformer. It was published in 2016, right? And 2 years later, Google proposed the BERT. BERT, the full name of BERT is Pre-training of Deep Bidirectional Transformer for Language Understanding. So BERT is bidirectional, and T means transformer. So this is a transformer for 2 directions. One direction is from beginning to the end, and another direction is from the end to beginning. So let's take a look. We are very familiar with ChatGPT. So what does ChatGPT mean? ChatGPT means this is the ChatGPT 1.0. Okay, it was published slightly earlier than BERT, 4 months earlier. ChatGPT means when they see a sequence of words, they predict the next one. And when the new word was added, then they use the original one plus the new one as a new input to predict the next one. So they only see from left to right. Okay? And BERT means they not only see one direction, they also see the sequence from the end to the beginning. So let's take a look here. So what is BERT pre-training means? It means given many sentence pairs, For example, this is one sentence, and they add a separation token, and this is another sentence. Sentence A and sentence B, there may not be any relationship between the two sentences, but they marked 50% or certain percent words, so it will become a closed question. If you only see its previous word or its after word, then they want to train a model to predict what should be the missing word from those existing words. Okay. So they need the bidirectional architecture, and they train a lot of sentences pairs. Then they will learn the model inside the BERT architecture. So this is a pre-training. Pre-training means if those parameters are learned, then they can use the pre-trained model and fine-tune it for some language text they want. So see, there are some language test example here. Squat, NER, and ND. I have to say, I'm not familiar with those language tests. And next semester, you are going to take a the language course, right? It will instructed by Professor Gung. Okay, and she is an expert, and I have no idea about it. So if you have a question, ask her. Okay. So what I want to say is, what is the connection between BERT and our vision task? Okay. So here is, okay, I should say, before BERT, there was another model called Elmo. And Elmo is just the name of this is a sesame puppy. Okay. Therefore, when they publish the paper BERT, okay, it is also happens again another puppy in Sesame Street. Okay, so we often see the icon here. Right? All right. Okay, so this is the paper published by Professor Omar's lab 2 years ago. Their idea is BERT, it is a model, is very, very expensive to train. And the BigGAN is also a model very, very expensive to train. Can they find a method? They do not need to train those models. They just use the pre-trained model to generate the images. Okay. Because BERT is a language model, and the BigGAN is an image model. So in this paper, what they do is to propose the method. Given a random signal or noise, and BERT and text prompt, then they can use BERT to convert the text prompt into a signal, and combined with the noise signal, they can use BigGAN to generate images. So that's what they want to do. Okay, so there are some examples. So this is, if they given this image, they will generate 3 different images because there are the random signals. Whether random or the noise signals are different, the generated results are different. Okay. All right. Okay, so let's see the sentence BERT. That is another paper. BERT is a model pre-trained using a lot of sentence pairs. And the sentence BERT, it means they want to use a Siamese architecture and use pre-trained weight in BERT so that they can create the vector representation of a given sentence. So to do this, okay, they need a data set. This is the Stanford Natural Language Inference data set. They are 570K sentence pairs. So this, and all of those sentence pairs are annotated. Are they neutral, entailment, or contradiction? So, given the sentence A and B, if they are neutral, then through BERT, they can generate, I should say, this is a fine-tune task. So there are some pre-trained model in BERT. They just need to add a few layers so that they can generate a sentence, a vector U and another vector V from the two input sentences. And if the sentence A and sentence B are neutral to each other, then the distance between the sentence A and the sentence B should be greater than another sentence A to sentence C. If the sentence A and the sentence C, their relationship are contradiction. Okay, so they use the idea. So this is called triplet loss. And they use the idea and train two data sets, the Stanford and the multi-natural language inference data set. So they can convert a sentence to a vector. And the vector can present the sentence in the latent space. Okay, so here, this is the training process for the network-to-network. They randomly generate some noise signal, okay, and use the noise signal plus, okay, use the noise signal and the BigGAN generator, so it can generate an image. And given the image, they use an existing caption model. What is it? It doesn't matter. And there are some existing methods. They can convert an image into a sentence. Okay, they just pick one, state of the art, and they get a sentence. And the sentence is generated by the image, and the image is generated by the noise signal. Then they use sentence BERT here, so that they can convert the sentence into a vector. What they propose is they proposed a conditional invertible neural network. And the conditional invertible neural network was not their invention. There is an existing method. Okay. And they put those components together. Okay. So the CIN can use the vector of sentence as condition and a random variable to generate the vector of input for BigGAN. Therefore, okay. And this is the structure of the condition CIN, and the architecture was proposed in this paper. Okay. So I say Professor Omar and his student didn't invent the paper. They just used the existing method. Okay. So once they learn the CIN, they can get the result given a random noise and given a sentence, and use sentence BERT to convert the sentence into a vector presenting the sentence. Okay. Let's see again. It means given a sentence, convert it to a vector presentation, And the user presentation and a random signal, they can generate the presentation of about input of the BigGAN. Therefore, this is the part. They put it into BigGAN and generate images. So, okay, see, you can see the whole process. And it also means before the release of latent diffusion, they have started for the language to text to image problem 2 years ago, and they are quite familiar with the conversion. In latent images, they use the sentence. They didn't mention what is the text to latent space conversion. They only mentioned they use some method in their previous paper. So I think that is the sentence BERT. Okay, so let's see some of their results. So given the sentence, they will convert, they will generate those images. And do you see? I should say, you can see something very similar to latent space. Latent diffusion. Input is text, output is image. Even though they use different methods. In addition to the qualitative comparison, they also show some quantitative comparison. So there is a dataset called COCO step. And in the COCO step, every image has a caption. The caption describes the image content. So there are some existing text to image method, the SDGAN, attention GAN, stack GAN, DN GAN, and mirror GAN, HD GAN. Okay, so that means they use the same content, the same sentence to generate the different images, so that they can compute the inception scores and FID values. They show their results is better than existing method in terms of ID, and almost as good as the result of SDGAN. Okay. And then they also show their method is use less computational cost. So to train BigGAN, it takes 15 days, and to train BERT, it takes 10 days on very good machines. But since BigGAN and BERT are well trained already, use their method, they just need less than 1 day and on a regular machine, and they can use much less energy and cost in terms of euro, and less CO2. So this is an interesting index. They can generate good or acceptable results. Here you can see they try to link the sentence, image representation and the sentence representation. So what does it mean? It means CLIP. CLIP aims to do the same thing. They want to connect the presentation of sentence and image. And CLIP uses a direction approach. Given a lot of image, they train the encoder and the decoder directly. And the network-to-network not. They use some. They didn't do it this way. They use existing architectures to do it. All right. So let's take a break. All right. So CLIP will directly address the problem Professor Omar's lab want to solve. They create the direct connection between images representation and sentence text representation. And this is very impressive. So after the paper was released, there are many people want to prove it, or they want to provide a public version because CLIP is a private, actually the data set to train CLIP is a private data set. Nobody else can use it. So the attempt, one of the attempts is they try to modify the architecture of CLIP. So you can see, if you use CLIP, you just use the image and the sentence directly. So the PyramidCLIP, they propose the method. Given the image, they not only use the image itself, they also create some local view. It means in the text part, they add more details about the image. Okay, and they also extend the image to different objects. Then, for the text part, they add more description. For example, the color of those pillars, the color of the sofa, etc. So you can see this is an extension of the CLIP. Not only the image itself, but many local objects or detailed description. So they train a model like image, like CLIP, and they propose their result. They show their results. Here, first, let's see the data set. CLIP used 400 million image to text sent pairs, and PyramidCLIP, as far as they can collect, they only have 143 million data sets. It is combined by 6 existing data sets. Okay. And this is the number of those existing image text pairs. And the largest one is Lion, 99 million. Okay. And here they show their results. So for zero-shot classification, on some existing data set, for example, the C10 means CFAR 10, C100 means CFAR 100. Okay, and so they show if they use CLIP and their implementation of CLIP, because the algorithm of CLIP is quite simple. Okay. The problem is the data set. It is private and nobody else can access. So they implement CLIP and train the model on their own data set. Okay, so those are the results. They show their CLIP can generate better results on many data sets. And for the average, their results are better than CLIP. Okay. And for linear probe means fine-tune. Okay. So it means use those training images of those data sets to tune the less linear, fully connected layer. Then their results are also better than CLIP. And after CLIP, there are some methods. For example, SLIP, FLIP, and declip are all modification of CLIP. And they want to show that their PyramidCLIP generated better results than those existing methods. So okay, this is PyramidCLIP. Okay, and then take a look of the time. PyramidCLIP was published in 2022 April, And okay, OpenCLIP. It was the clip version released by Lion. Okay, because Lion has a huge data set, they can do the same thing and use more data set rather than CLIP. CLIP is 400, and median has at least 2 billion text to image data sets. And so that 8 months later, Lion released the OpenCLIP. Okay, so let's see, take a look here. CLIP used 400 million training samples, and OpenCLIP, they use 2 billion. If they use the same architecture, the L14 means vision transformer use patch size of 14 by 14. And the vision transformer has at least 4 different settings: base, large, huge, and giant. Okay, so if they use the same architecture and train more images, then on image set, the performance are slightly worse than CLIP. And for VTAB Plus is Vision Task Adaptation Benchmark, and there are 35 data sets. And the 35 data sets was extended by a paper. The paper means called VTAB, a large-scale study of the. Okay, there were only 19 data sets, and in the paper of OpenCLIP, they extend the 19 data sets to 35. Okay, and this is the list of the 35 data sets from ImageNet to Kitty closest vehicle data set. Okay, but they shows on the COCO data set that their results are better. And if they change the architecture to use transformer huge, their performance are better than CLIP. Okay, so let's see a chart. The chart is not very easy to read, but let me explain it. Okay, CLIP released 3 different pre-trained models. Okay, so it is see the red, blue dot, 1, 2, 3. This is the small CLIP, medium size CLIP, and a large CLIP. They use different transformer architectures. The small one uses VIT base and with 32 by 32 patch size or 16 by 16 patch size. The larger the patch size, the shorter the sequence of the vectors. So that the model of the size also becomes smaller. Okay. And so here you can see the line. That is the connection between the 3 models of clips. And okay, the 2 images are trained on 2 different data sets. The one is ImageNet, and the other one is ImageNet robustness. It is a variation of ImageNet. It means you see, you know, there are 1,000 cases of ImageNet, and ImageNet robustness, it combines 5 different types of image sets. Do you still remember that? ImageNet R, ImageNet A, and ImageNet forgot the remaining 2. So it means, do you remember there is a chart with a banana? The banana image in imaging set usually is at the center, and the shape looks good. But the banana in image A data set, it looks somehow article. Okay, very not the natural the banana, maybe the drawn or sketched banana. Okay. So let's see. Okay, for the OpenCLIP, okay, they also try different models, and the largest one is the VITG. It means the giant, the largest one. And okay, they train the models on different data sets. Lion 18 million, 400 million, or 2 billion. So that the 2 billion you should see the square one. So this is trained on the 2 billion square. And the color means the different VIT architectures. So the largest architecture with the largest data set is this one. Okay, so it generates the best results. So it makes sense. And you can see there are two different slopes. It means the difference between Lion data sets and the VIT data set. Okay, it clearly shows if you train on the two different data sets, the VIT data set, the quality of a VIT set is better than Lion because the slope is larger. Okay, so it makes sense because the Lion data set is collected by images from internet. Any kind of images, they cannot control the quality. Good sentences or poor sentences, all of them are collected in the Lion data set. But for the VIT data set, they don't know how OpenAI compile those data sets. If OpenAI applied some filters to remove the low quality sentences, although there are only 400 million samples, okay, they can generate better results in terms of with respect to the number of training sets. Okay, now we are going to our second track. Let's see. Let's continue the one we talked about last week. So let me show you the. Okay. So the second track is this. After VQGAE, it was used to VQGAN. And the VQGAN is the second paper released by Professor Omar's lab. Okay. So here, they try to create, for network to network, they try to create images from text input. And for VQGAN, they try to generate image from latent space. And what is the latent diffusion? Latent diffusion means they try to create an image from text through latent space. So latent diffusion, it can be viewed as a directly combination between their two previous works. So let's go back to VQGAE and VQGAN. Okay. In previous week, we talked about VQGAE. It means given two images, given one images, the method want to create an autodecoder so that the image can be encoded in the latent space and decode back to its image space. And VQ means vector quantized. The latent code are discrete rather than continuous. There is a code book. All of the latent code can only be one of the instance in the code book. Okay, so why do they want to do it? What is the advantage of using the quantized vector of the autoencoder? Okay. Okay, their idea is in our language or in the ImageNet classes, the classes are discrete. They are not continued. And for our language, our words are discrete. They are not continuous. Okay? So that's the reason they want to develop a quantized variational autoencoder. First, they show although those latent codes are discrete, they still can reconstruct the image well. So that's first they show. Okay. So the left part is the input image, and the right part is the reconstructed image. They are visually similar to each other, so the loss is very small. They show it is achievable. Okay. And they also show because they convert an image into quantized vectors. So it means in the latent space, AV signal is discrete. So what does it mean? It means if you can predict those latent code, you can reconstruct the image. So it becomes a generative model. Let's show it again. Here, if you can predict those latent code, they are discrete, they are limited, they are not infinite, they are only some choice you can predict. Okay, and if you can predict one after another, and you can reconstruct the latent code. Once you reconstruct the latent code, because you have a trained generator or decoder, then use the latent code, you can generate an image. So it becomes an image generative model. Okay, so how to do it? There are some existing methods called pixel CNN. Pixel CNN means if you know some existing pixel, like the one in this patch, and you want to predict the next pixel, then if you can do it, then you can generate an image. So this idea can be applied to the VQGAN. Okay. Okay. So they also show VQGAN can be used to render synthesize the voice. So we stop at this slide, previous work. It shows given an input signal of voice, okay, they can convert the input signal into the latent space. And if they use two different decoders, they can create two different voice signals. And the message or the words in those two signals are the same. But the voice sounds different because they are generated by two different decoders. All right, so here, what is the VQGAN work? So this is architecture of VQGAN. And the VQGAN, this part, it is the encoder. And this is the decoder. So from here to here, it is just a VQGAN. And but they apply a GAN architecture here, so that they try to ensure the generated images looks like a real image. So what is the innovation of VQGAN is here. They use a transformer to predict the next latent code. So from VQ Pixel CNN, how they predict the next pixel value. Okay, that's it. There are many possible approaches, and VQGAN try to use transformer, and the transformer in around 3 years ago. Okay, it is relatively new. Nobody else used transformer to VQGAE. Okay, so they are the first one, and here the transformer works very like a GPT. Why? Because for GPT, we have a given sequence. Then we want to predict the next token. And for VQGAN, it's the same. Given a sequence of existing latent code, they want to predict the next. Okay, so they can train the they can train the transformer on a existing data set for, say, ImageNet, so that given some latent code, they can predict the next one, and then they can generate an image through the decoder. Okay, so this is a two-stage training process. The first stage, they need to learn the vector quantization. Okay? So what is? So given the image, okay, they develop the encoder. So the encoder will convert the image to the latent code. So the latent code is not a vector; it is a tensor. Okay. So for the resolution, it will reduce by a factor of the factor is didn't show the factor. Okay. And they design a code book, and there are K latent code in the code book, and each of the code is in the dimension of NZ. Okay. And then quantize means when they convert the image into a latent space, they need to pick up the one mostly similar to the one in the latent code book. So here is a differentiable step, and then they will reconstruct the image from the latent space through a decoder to get a reconstructed image, and then they define their loss. The first one is the vector quantization loss. Okay, it means the reconstructed image has to be similar to the original input one, and there are some stop gradient operation because the quantized step is not differentiable. So the gradient will stop here. So they create a loss term here. And the second, they need to they create a GAN loss. The reconstructed image needs to look like real image. Okay, so they optimize this term. And pay attention here. The optimization term doesn't include the discriminator. Usually, in our GAN training, we will train a discriminator and a generator. But here, they give up the training of discriminator. They just use an existing discriminator. They don't care about it. They believe discriminator, some existing discriminators are good enough. So they pay their attention to train the encoder, decoder, and the code book. Okay? And in their training step, they prefer to learn perceptually similar results. So they use LPIPS as a guidance to update their weight parameter lambda. Okay. And let's see, this is the architecture of their encoder and decoder. So given an image, they use convolutional network, and through several residue blocks, then there is a non-local block. So what is non-local? We have seen it before. It is just the attention, self-attention maps on a certain feature maps. Okay. So the encoder in their paper they claim the encoder is almost the same as the DDPN's architecture only without a skip connection. Right? Okay, so this is the second stage. They need to train the transformer because this is the VQGAN, but they still need a transformer to predict the next latent code. So in the second stage, they use the sliding attention window. For a region, if they see some existing latent code, they want to predict the next one. And when the new one is predicted, they use the existing one and the new one to predict the next one. So this is called auto-regressive approach. So in pixel CNN, the same. This is also an auto-regressive approach. Okay. So that means, given some existing latent code, they learn the transformer to predict the one. So the loss of the transformer is this. So the X is a given input, and there is some distribution of the image classes. And then they want to minimize the multiplication of those probabilities. Okay, so let's see. For different data sets, they use different settings. Okay, so here the RIMS restrict the image net, and the DIMS depth map restrict the image data set. So it means, in addition to the image, they also provide a depth image. So they can learn how to predict the latent code from the depth image. And the ImageNet is the one we are familiar with. ImageNet is the class conditional. And S flickers semantic flicker, then okay, what is S flicker? This looks like S1. It is a landscape image, and there are some semantic map available. Okay, and those images are usually very large. So this is a resolution 128 times 832. This is the interest part of this paper. Their method can generate a high resolution image. Just use VQGAN. Okay, so for different data sets, they set different layers. So this is the layers used in the transformer. So and this is the parameter. The largest one is the conditional image, and the class conditional image net with big resolution. So the parameter is also larger. Okay, and okay, so let's see some of their results. So this is the S flicker, and okay, so here, this is the image data set. For this, they can crop a region and using the remaining part to generate the results. Why? Because once they can see this part, their transformer can predict the next latent code here. And again, then they can reconstruct the image. For the restrict image data set with depth maps, then given a depth image, once their transformer was trained to learn the relationship between image and the depth map, then they can generate a different result. So you may ask, why are they three different results? Okay, let's go back here. You can see this is the autoregressive transformer, right? But if the first token is different, then what will be the remaining tokens are all become different. So that is the reason they can generate multiple different images from the same text image. Okay. And also, this is the segmented guided. So this is an example of a segmented image. It's like this one. If you give a segmented image, tell your image generator there should be mountains, there should be rivers, and there should be sky, and there's some grasses, then it can reconstruct the image like this. Also, they can convert a pose image into a realistic image, and also class conditional. Okay, if we see some example here. So this is the class conditional images in the ImageNet result. Some of them looks good, but you can see the face, because human eyes are very sensitive to faces. So there are many artifacts here. Okay. So therefore, they need to find the optimize the parameter for this method. Okay. So you can see there's an important factor means scaling factor. The scaling factor used in here. The original resolution is height, time, width, and when it converts to the latent code, the resolution is only small h times small w, and the scaling factor is the f. F means the capital W divided by the small little lowercase w. So okay, let's try different scaling factor. So for f as 1, it means they use the same resolution. Okay, and they try different scaling factor 1, 2, 5, 16. All right, and okay, this is the okay. So when using different scaling factors, the process, because if the scaling factor is small, it means there are many latent code. You say the latent map is very large. See here again. If the f is 1, it means the small h is the same as the large h. So the latent image is very large. Okay? And when the scaling factor is very large, the latent image is very small. Okay? So there is a speed up. It means if we need many times a period of time to generate a result for f1, then if we enlarge the scaling factor, the process, the time we need only is much shorter. So the ratio is the speed up. However, okay. So let's see some of their experimental results. So for the select AHQ 556 square, they generate a good FID, but not the best one. And for the FFJQ dataset, they also generate a good result, but also not the best one. Okay. And however, compared with DALL-E, I will show you what is DALL-E, the first version later. Okay. they want to show that their method can generate their method generate a better result than DALL-E. And here is a parameter k. Let's go back to the BigGAN. Do you remember? Let me show you the truncated normal. Here, if you reduce the available range of the noise signal, you can generate a you can improve the fidelity, but you will lose the variety. Here, the k is almost the same. Okay. If you set a large k, then you will generate a highly various results. If you set a small k, the generated images look like, I should say, their perceptual. They are perceptually similar to each other. Okay, so let's talk about the first version of DALL-E. So it is based on this paper, zero-shot text-to-image generation. Okay, and the method is very similar to VQGAN. Okay, because given they convert image into a latent space and also the discrete latent space. So in this approach, they are identical to VQGAN. But what's the difference is they don't have a discriminator, and they have a transformer, but the transformer is conditional on text. Okay, so in VQGAN, the transformer is conditional on classes, depths, or skeleton, or etc., or sentence semantic maps. But DALL-E can condition their input as text. What's the reason? Let me show you the reason is because DALL-E was released by OpenAI, and OpenAI has the CLIP, right? And if you read both paper, CLIP and DALL-E, you will find that more than half of the authors are the same. What does it mean? It means the teams create a CLIP. They just slightly modify their CLIP, and they can apply the result of CLIP to image text-to-image generation task. So that is DALL-E. All right. So this is the result of DALL-E. Given a sentence, they can generate those results. Another sentence, they can generate those results. Okay, looks quite good. And they also show the second row is the result generated by DALL-E. And the first row is the reference image. You can think then as a ground truth image from the COCO dataset. And there are some existing methods, DFGAN, DNGAN, and ATTGAN. You see the 3 GANs in the table. Do you remember it? Okay. Okay. And given those sentences, they can generate the images like this. So visually, just visually comparison for the giraffe, it looks better than the existing method. Okay. And okay, so all right. So okay, now we are going to talk about the latent diffusion. So see, this is the architecture of latent diffusion. Here, this is a latent space from VQGAN. Given the image, there is a encoder and a decoder. Okay, and here is the latent space. It used a diffusion model to solve And the diffusion model comes from the ADN. ADN is the diffusion model BigGAN on image synthesis. Okay, and this is a conditional. So this conditional, the text encoder in their paper, they claim they from transformer. But what does this mean? They didn't provide further details. But what I think is the transformer just a sentence BERT. So the sentence BERT was used in their first paper 2 years ago. And the VQGAN was their paper published 1 year ago. And they combined the two and replace, I should not say replace, they introduce the UNet, okay, used by ADN, because the UNet contains self-attention. So they just combine those components together, and it becomes the latent diffusion. Okay. So when you read the paper, when I read the paper, I found a very interesting thing. They didn't mention what is the innovation of the paper, but they emphasize what is the social impact of the paper, the method. What does it mean, social impact? It means before the latent diffusion, the available methods include DALL-E or DALL-E 2. They are very huge. Nobody else can train it, can reproduce their result. Only the big companies, Google and OpenAI, can have so much computational resources to do this. But with their latent diffusion, many researchers can use the model because their model is relatively small. It can easily run on consumer level machines. So this is a social impact. Their method allow many users generate images from text by their own. So that is the most interesting thing when I read the paper. Okay. However, we need to mention about this mathematical definition first. So here, given the image, so when you see this sentence, it is very similar to the VQGAN. It converts the image into a latent space. So the scaling factor f again occurs here. Okay. And for unconditional case, they just reduce or optimize the process, the diffusion process. So this is the latent diffusion model. So this is a diffusion model. Okay. They need to learn a noise predictor epsilon theta, so that they can predict the latent code in the previous step. Okay. So that's in BigQGAN. This is a transformer. In latent diffusion, this is a diffusion step. Okay. For conditional case, they just consider a conditional vector y. And however, for different tasks, they need to learn different conditional encoder. So the tau theta means it will convert the condition. It can be a label in the ImageNet. So there are 1,000 possible labels. And it can also be text. So if this is text, it becomes a text to image generator. All right. So let's take a break now. All right, so okay, we talk about for different tasks, they need to train different conditional encoder, okay, and they convert the condition into a intermediate representation. Okay. Then in their UNet, so the UNet comes from ADM. Okay, this is the UNet contains the attention layers. So for attention layer, there are 3 inputs: query, key, and value. Okay. So the attention is computed from query and the key, and finally the value will be used to generate the new sequence of a new matrix, I should say. Okay. So the definition. So they generated their Q and from the latent code, and they generated their K and the V matrix from the condition. So this is called the cross attention, right? Okay, then let's see their settings. Okay. So this is the unconditional case. Okay, it is compared with the VQGAN and the DALL-E. Okay, so use different scaling factor f and the codebook size. Then and the different channel, it will generate different results. Okay, and what is the KL means? The KL means the KL divergence. So for this column, it uses VQGAN. It actually the encoder generates discrete quantized vector, but for the KL case, it generates continuous vector. So they show the table means for their method, it no longer restricted to discrete space, because in VQGAN they need a discrete or quantized vector because they use transformer to predict the next vector. But here, since they use diffusion model works for continuous space, so they train different the 2 different models and show their results. Okay. Okay, and then if here when they do experiment on the level 8 data set. Okay, so this is the latent diffusion model 1, 2, 4, 8, 16, 32 means the scaling factor. They found the scaling factor is a very important hyperparameter. So this is just the table to show the settings. And here, if this is another table for the ImageNet data set. Again, you can see the scaling factor 1, 2, 32. That's okay. Just keep it in mind. All right. So let's explain the 2 figures. So this is the result of the select A data set and the train 500K step. So let's see for different scaling factor 1 to 32. So this is the scaling factor is 1. The FID value is very high, and this is the 32. The purple. This is 16, and this is 8. This is 32. Okay. So when we use a large scaling factor, it means the latent map is very small. Because the latent map is small, the throughput, it means for a second, how many samples or how many images can be generated from the model. of course, I should say, we can see the latent LDN32 generator the largest one, because the latent map is very small. And there is another parameter. It means the step used in DDIN, because there is a diffusion model contained in the latent diffusion. Okay, so they need I should say, noise predictor, or you can say it's a score estimator. It's just this. They need to learn the epsilon theta. It means given a latent code and a step number, and they need to predict the noise value. So for different settings, from 200 to 10, okay, you can generate from the same setting, you can see different results. So what does it mean? If you use 200 steps, then your FID is lower. Why? Because the more steps, the better the quality from one step to predict the noise to the previous step. But however, if you use 200 steps, then you will reduce the throughput. Because if you just use 10 steps, you can use only 1/20 time to generate the same number of results. Okay? So this is the performance is consistent for different scaling factors. If you use more steps, you need your throughput. You takes more time to generate one image. Therefore, your throughput becomes smaller. Okay? And it's the same for the ImageNet datasets. Okay? So let's see another figure. So the same. This is the different scaling factor. And here, it means if we train so many steps, how good is the performance for different settings? So let's see, the blue one is the FS1, the orange one is FS2, and the green one is FS4, and the red one is FS8. And if you see, okay, the purple one is 6, and the brown one is FS32. So you can see a trend. If you use very small scaling factor, your FID is not the best. If you slightly increase your scaling factor, you get better FID. But if you use a very large scaling factor, you get a bad FID again. So the scaling factor means what? It's a trade-off. Why? Because originally you have a input image, and the resolution is high. You reduce it to a relatively small latent map, and it's controlled by the scaling factor. If you use too large scaling factor, then your latent map will become very small. It cannot contain too much information because the resolution is too high. Okay? But if you use a very small scaling factor, then it will become a difficult problem for the diffusion model because there are too many pixels to need to be predicted by the diffusion model. So they show the two figures to show there is trade-off, and for them, it is important to pick up a good scaling factor for their experiments. All right, Okay, so let's just take a look of their results. So this is the Celeb AHQ and FFHQ, and on the ImageNet of the resolution 250 square, looks good, I should say. And this is the LSAN chart, LSAN pad, and the ImageNet dataset, and the results looks good. And all of them are unconditional. So it means in the architecture, they remove the conditional part. They just want to use the latent diffusion model. It can generate a very good result. So that's all. And it's not surprising because there are existing paper. Okay, let me show. This one, diffusion model BigGAN. It shows already diffusion model generates a better result than GAN. Okay? And the latent diffusion was published lately than this one, so it's not a surprise. Okay, so let's see the conditional setting. So they can generate the images from semantic map, from encoding super resolution or class label, and the layout and the text to image. Semantic map to image, you know it already, right? Because it was used in VQGAN. Okay, so here, the most interesting part for me is the text to image, because in VQGAN there is no text to image. Only in latent diffusion they apply a encoder so that the image can be conditioned on text input. And you can see here, because they won't need to convert the text to a latent to a conditional code. So the model size is the largest one among all other conditional tasks. Okay. And let's see some results. So these are good results, I believe. Otherwise, they won't show them on the paper. So given a text, given a text sentence, they generate the results. Here, when you see the capital, you see there is an unconditional guidance. I need to explain it. What is the unconditional guidance? And if you use diffusion model for your homework 4, there is also a, okay, let me see whether I can find it. Sorry, I did it. Okay. The factor also exists on the user interface. It is called guidance scale, but it doesn't mean unconditional guidance. So let me explain what is the unconditional guidance. Okay, so let's go back to DDIN. Oh, sorry, there is another parameter eta. So they mean they use DDIN 200 step with eta as 1.0. So what is eta? And this is the slide that I used previous week to explain DDIN. And in DDIN's experiment, they define the sigma as the eta times the two terms. If the eta equals to 1, it is DTPN. If eta equals to 0, it is DDIN. So let's go back here. In their experiment result, they set eta as 1. What does it mean? It is DTPN. It's just DTPN. Even although they mention this is a DDIN model with 200 steps. In fact, it is a DTPN model with 200 steps. Okay. But why they need to mention here? Because in their paper, they not only show these images, they also show many different images. So you can see there are 1, 2, 3, 4, 5, at least 6 different settings. And for some settings, they use DDIM, and for some settings, they use DTPA. Okay. So therefore, in this text-to-image experiment, they use DTPA. Okay. All right. And now let me explain what is unconditional guidance. Okay. So there is another. Okay. Let's just skip it. This is another setting. Okay. Well, let me explain this figure at first. So this is their setting for the transformer. It just means the encoder for text. So this is a transformer, and it can accept at the most 77 watts. And the depth of the transformer is 32, and the dimension is 1020. 280. That's the reason the model for text to image latent diffusion is very large because of the transformer. So they also show the comparison. So the DN K means the K divergence, and the 8 means they use scaling factor as 8. So this is their picked result. The test G means the guidance. One with guidance, and the scaling factor guidance scalar is 1.5, and another doesn't use the guidance score. So the one with the guidance score generates a better result. And this is, I think this is the most important color here. This is a number of parameters. Their model, even for the text condition, there are only 1.45 billion parameters. But see, this is a glide. Glide is the paper for DALL-E version 2. This is DALL-E 2, okay? And for DALL-E 2, they need 6 billion parameters. So it is 4 times of the LD, latent diffusion. So latent diffusion can run on most consumable machines. But DALL-E 2, even though OpenAI released the pre-trained model, it is very difficult for most users to run the model on their own machines. Okay, so that is the reason why in the paper the authors talk about their social impact. And so this is the number to support their claim. Okay. Now I'm going to explain what is the guidance scale. Okay, so let's go back to the history of stable diffusion. Here I just want to show you they released many different models at a different time. From version 1. So this is stable diffusion, not latent diffusion. Okay. Stable diffusion is based on CLIP, but the latent diffusion is based on the text encoder trained by themselves using I forgot the version, Lion 200 or Lion 80 or Lion 800 million, forgot. Okay. However, what I want to show is, okay, so this is 2 figures cropped from the official website of Stable Diffusion. So this is the different for a curve. It means a different Stable Diffusion model, and you see there is different classified free guidance scales. the classified free guidance scales is the guidance scales we see in the paper. This is the value. Okay? And here they want to show is this is an important parameter. Okay. And I remember some of you mentioned this parameter in your homework 4. It means I forgot which one to it. If you set the guidance scale very large, you will generate oversaturated images. Okay. And they want to show for any stable diffusion version, the parameter is very important. If you set a good parameter from between 1.5 to 8.0, it matters and it affects your generated results. Okay, so let's explain what is the guidance factor. We need to go back to the paper, diffusion model BigGAN on image synthesis. So okay, so let me just quickly go through it. So they want to modify DDPS unit, and they found, okay, if they use an existing classifier in the image for the ImageNet dataset, and they use a scaling factor for enlarge the gradient of the generated by the classifier, then okay, they generate quite good result. So this is the scale factor. If this is 1.0, the FID is large, and if it's set at 10, then FID is small. And this is a visual comparison. For the left side, it means the guidance scale is 1.0, and for the right side, it means the guidance scale is 10. So visually, what tells us? It means if they apply the scale, and where does the scale come from? The scale comes from a classifier, but the classifier is not a part of the diffusion model. It is an external part. You can borrow it somewhere, but it is not part of the diffusion model. However, after using the classifier, we can generate the images which match our, I should say, expectation. Okay. For example, the corgi. Okay. Yes, there are corgis in these images, but they are not so clear, so obviously, or they are not so large. But if we set a very relatively large scaling factor, then we can guide our diffusion model to generate the latent or the latent code or the image preferred by the classifier. Okay. And if the images are preferred by the classifier, they usually also preferred by users. However, there's a problem. The problem is the classifier doesn't belong to the diffusion model. So in 2021 December, okay, the Jonathan Ho and his colleague published a classifier-free diffusion guidance. So who is Jonathan Ho? Jonathan Ho is the first author of DDPN. So he is the expert for diffusion model. He thinks, or he believes, it is very confusing. If we use an additional or an external classifier to guide the diffusion model, okay? So they propose a method generate similar results, but they do not need an external classifier. So let's take a look at their approach. So this is the definition for a classifier guided diffusion model here. So this is the thinnest one. Okay, so this is the paper published by OpenAI. Okay, you see here they apply a scaling factor to the term of the gradient of a classifier. Although they use different symbols, the meaning is the same. So here, they use the symbol W. It means the scaling factor. Okay. And it also applies to the gradient of the classifier. So the classifier is the P theta. Okay, so this is the existing method. So what they propose is they generate the guided predicted noises, but they do not need the classifier. They just need two noise estimator. One is the conditional one. Another is the unconditional one. So what does it mean? It means for ImageNet, okay, what is the conditional one? They need to train a diffusion model using images. All of those images belong to the same class, for example, Corgi. Okay, and unconditional ones, they train the overall images in the image data set, so they become unconditional. Once they have two diffusion models, then they can generate two predicted noise and use the two predicted noise as the new predicted noise. So that they can generate similar results. So let's see their experimental results. Okay, so the ADN is the diffusion model BigGAN, the one proposed by OpenAI. And the CDN is another paper. Okay, it is the previous work of Jonathan Ho, cascade diffusion model. Okay. And then if their model without the guidance, the FID is worse. And but if they apply the guidance value, then the FID continually increase because the new distribution will be dissimilar with the existing distribution, just like this one. Okay, so suppose this is the original distribution, the training images. Okay, there are many Corgis in the images, but they are not clear. But when they apply the guidance scales, the dog become very obvious. But the new distribution will be different from the original distribution. Therefore, the ID value increased. Okay. And okay. However, because the new image contains very clear Corgi, so their inception score increased. Because inception score is the index that a classifier can easily recognize the object in the image, or I say they can easily classify the image. Okay, now you have a very big obvious Corgi in the center of the image, so it will be easy to recognize. Okay, so they draw their results here. So you can view it as a trade-off. If you want clear, obvious image, you will have very high inception score, but you will alter the distribution. So your FID will also become larger. Okay, so Jonathan Ho proposed his method for image net, and the condition for image net is the class label. But for text, when we have a text prompt, what will happen? So, for example of latent diffusion, the condition of the noise predictor is the diffusion model with text prompts. And the condition of the noise predictor is if you do not key in any text prompt, you can still use latent diffusion to generate the images. So that is the condition of the case. Therefore, when I should say, okay, let me show, okay. Jonathan Ho's classifier-free condition guided scale originally applied for class label, and it can be easily extended to text prompt. Okay, so this is the result generated by its method. So this is the image net, and he only generated small images, 60 by 64. The W is 0, W is 1, and W is 3. It means the same class, the same seed, and with larger scaling factor, guidance factor, you will see clear image. For example, this is a dog, and in this one, this is very clear. So it is they just show those images to illustrate. Yes, that's what the expected result. Their classifier-free guidance can do as well as the classifier guidance scale. So this is another example. When we enlarge the guidance scale, we see many clear or obvious Malamute dogs. Okay. So now let's explain what DALL-E version 2 do. Okay. So DALL-E version 2 is used in diffusion model. This is ADN. ADN just is the diffusion model BigGAN. Okay, and it uses classifier-free guidance, Jonathan Ho's method, or CLIP guidance. Therefore, compared with DALL-E 1, okay, DALL-E 1 is just the VQGAN work. They use a transformer. No, they use CLIP to predict the next vector quantize and generate the image. So DALL-E 2, because they have the ADN module, so there are 2.3 billion parameters there. And the ADN module only can generate images for 64 by 64. It's a very small image. So they need 1.5 additional billion parameters to do a super resolution task. And the text conditional transformer, just very similar to CLIP, it also requires 1.2 billion. So overall, DALL-E 2 needs around 6 billion parameters. Okay. And these are the results of DALL-E 2. And this is DALL-E version 1, the third row. And the fourth and the fifth rows are the results of DALL-E version 2. The difference is for row 4, it uses CLIP guidance. And for row 5, it uses classify-free guidance. And okay, so they ask users, which one would you prefer, DALL-E version 1 or DALL-E version 2? And this is a human subject study. 97% users feel DALL-E 2 generate better images in terms of photoreal. Okay, and 69 think DALL-E 2 generate images close to, more similar to the caption. And they compare the performance between the two different guidance. One is CLIP guidance, and another is the classifier-free guidance. Okay, so let's see the precision and the recall. So this is the classifier-free guidance. For precision and recall, both numbers, the higher the better. It means when you see different settings, the blue one performs better than the original or orange one. Okay, so it means the classifier-free guidance is better. And if they measure the inception score and FID, for FID, the smaller the better, and for IS inception scores, the higher the better. So it means the orange, the blue one is better than the orange one. But however, if they use CLIP score, then they generate another FID and CLIP score. In this case, CLIP guidance is better. So it makes sense because CLIP guidance use CLIP to generate results. So their CLIP scores are better. So let's recall what is CLIP score. CLIP score means there is in CLIP there is a text encoder and an image encoder. Text encoder will generate a vector to present the text, no, the sentence. And image recorder, okay, let's go to the figure. Okay, here. There's text encoder and image encoder. They both generate a vector representation. Then the text score just means the inner product of the two vectors. Okay. So it means the higher the image and the caption will similar to match to each other. Okay, and in their paper, they show something very interesting. This is the failure cases. So if they give the sentence, a cat with 8 legs, no, they still generate the cats with 4 legs, and a mouse hunting a lion, no, they still generate the images a lion hunting a mouse. So it means some sentences do not work for their models. Okay. Their models cannot generate images out of very real or out of the concept. And here you see the metric of precision and recall. And let me show you what they are. Okay. So it is a metric to measure two distributions. Okay. This is example. If there is a generated distribution PG and the real distribution PR, then the definition of precision is how many generated images looks like a real, and the recall means how many real images can be generated by the generator. Okay. So this is a paper proposed by proposed here. Before this paper, there is another paper. Okay. this one. Assessing generative models via precision and recall. And this one is the improved version. Okay, so they proposed a different method. It means they use k-nearest neighbor to measure the precision and recall. So they randomly sampled many images from the generator and the real distribution. Then they define a function. The binary function is either 1 or 0. If they can find similar images from the distribution, and the distance is shorter than another one, so it means, okay, it is belong to the real distribution. So after the definition, they can measure the precision and recall. So this is very easy and straightforward. Okay. They show their the property of their method. First, with sufficient sampling, okay, and they measure they generated the vectors using VQGAN. Then, with sufficient sampling, the precision and recall stably converged. No problem. Okay, and there is another important parameter, is k, in the k-nearest neighbor. Okay. It means if you use different k, and you use the truncation, okay, then you can see they are, for different k, they consistently increase or consistently decrease. It also shows their performance, no problem, it's good. And then they show, compare with the existing method, okay, they show 4 sets of images. A, they are almost the same. This is a neutral phase, okay. And B, the image, those phases are slightly diverse. And those images are generated by the style GAN. There are several versions. This is the first version. So with the 4 set of images, when they measure the precision and the recall, there are 4 points here. 1, 2, 3, 4. It looks very good. Makes sense. If you have a neutral phase, if all images are neutral phases, then your recall is very low, but your precision is very high. Okay, and with different diversity among those phases, the precision is slightly reduced, but the recall slightly increased. But the most important thing is here. They compared with the existing method, and the precision and the recall, they cannot tell the precision recall among B, C, D sets. And for the precision, so it shows their improved the precision and the recall definition works better than the existing one. Okay, now you have the concept of latent diffusion, and the easy diffusion version 3 is based on latent stable diffusion version 1.5, and stable diffusion 2.0 has released, and there are some new features. First, it can generate a higher resolution. 1.5 only generated resolution of 512 squared, and now it is 300 and it's 1.5 times larger. Okay. And also there is a upsampling or super resolution module. They also provide a structure preserving module, so it's conditioned on structure. So this is useful interesting feature. And depth to image. Okay. Although we see the depth to image from the latent diffusion, but in the stable diffusion, they didn't implement the function. And now in 2.0, yes. Okay, so there is a waifu diffusion. So what is waifu diffusion? Some people, they want to generate a beautiful comic characters, but okay, they can do it now because of stable diffusion. So okay, based on stable diffusion 1.3, and they also based on stable diffusion 1.4, they collect image data sets. There are 680K text to image sample. All of them are comics, and they compile the data set from a Buru site. It's a website. Okay, on the website there are abundant comic images, but they also need text. So when they compile the data set, they use the machine. It looks quite good machine because there are 8 A40 and 22 high-end GPUs. They trained for 10 days. Okay, and it takes around 120K new Taiwan dollars to create the model. But however, interesting is it is feasible. If you want to, this is not a company. It is just a community of fans. They enjoy the training process, and they generate the model. So I remember some of you use anything, right? Anything for your homework for. It is something like this. Okay. And then they also enlarge the training set to 5.4 million image data set and tune it on stable diffusion 2.1. So that's the message delivered by the authors of latent diffusion. This is a social impact. They let users can create their own models. Okay. All right. Okay. So let's record this. 3 months ago, there was a seminar, right? And the professor from National Charlton University, he gave a talk, used this stable diffusion. So now you have the sense of stable diffusion, so that you can understand what he wants to do. Okay, let me slightly explain it. It means, given a sentence, okay, if you use stable diffusion, you will generate some images inappropriate. And there are some existing methods. They can prevent those sensitive prompts so that it can generate images without the concept that you don't like. And they developed a method to modify the prompt. So this is a prompt engineering work. Use the same safe model, they can still generate the nude images. So, okay. And this is their approach. So, given an image, a sentence, if they can generate nude images, they can use the encoder to get the latent code. So, that is latent map. Okay? And because of the stable diffusion, they can generate a noised one. And from the noised one, they can use some method to find the prompted. Okay, it looks ideal. Oh, it looks safe. But when you use it, you will generate bad results. Okay. So now you have the concept and you can understand what he is doing. All right. So that's the talk today.